Okay, now in the case of working with first order linear differential equations, we have various types of applications concerning working with items, leading up to the use of the integrating factor, and some of the applications might include finance as well as engineering courses that might involve material balances. And one such type situation could be for what we have in the case of mixing tanks. And looking at what we have here, okay, we have in this leadoff example, we have 1 kilogram per liter of salt entering a 1,000 liter mixing tank that contains 100 kilograms of salt, and the 1 kilogram per liter of salt, okay, is entering at a rate of 5 liters per second, and the exit stream is also running at 5 liters per second. And we have posed the question, okay, how long will it take when the amount of salt in the tank is 900 kilograms? Okay, so you have 100 kilograms of salt in the tank, and we're looking at 1 kilogram per liter of salt entering that 1,000 liter tank, and you have the rate at 5 liters per second, and you had the exit stream likewise. Okay, so just to kind of give you an overview. Okay, so you have with the tank itself, and this is a very crude sketch, okay, but you have like in the case of a mixing tank, and you have going in, you have the entering flow stream, you have 5 liters per second, and the exit flow stream, you also have a 5 liters per second, and we have going in, okay, you have 1 kilogram per liter of salt. Okay, so you have the in stream, and we have the out stream, and just kind of give you an intro to the components we have. Okay, so we'll say that we have X is equal to the amount of salt in the tank and of course T is going to be the time, which we're ultimately going to be solving for. And just setting things up here, okay, along the lines of working with differential equations. So you're going to have the amount of salts in the tank is going to be changing with respect to time. And the change is going to be the difference, okay, between what is going in and what is going out. And now you had the same volumetric flow streams, but I'm looking at the change up in terms of the amount of salt that is present. Okay, so we have just doing a bit of modeling. Okay, so for what we have going in, okay, so we have 1 kilogram of salt per liter. And we have for the volumetric flow stream, again, we have 5 liters per second. And if you notice, okay, we have in terms of the salt, okay, so we're looking at 5 kilograms of salt per second entering the tank. Now for what we have going out, okay, now we're going to have X kilograms of salt Again, X is continuously changing. And again, the volume of the tank is 1,000 liters. And again, we have the exit flow stream at 5 liters per second. Again, we had the liters to cancel out. And so for what we have exiting, we have 5x kilograms of salt. And we have with the unit cancellation between the liters, numerator and denominator. Okay, so we have 5x kilograms of salt over 1,000. And if you notice, we have for this ratio, you got 5 over 1,000. And we can just simplify this to x over 200. All right, so just looking at what we have in the overall picture. So going back to our equation. Okay, so we got dx over dt is equal to n. So you have 5 kilograms per second of salt. Now I'll just put in the numerical amount, and you have x kilograms, or x over 200 kilograms of salt per second exiting. And I'll just say that I have minus x over 200. Okay, so here we have in the setup, we've got a first order linear differential equation. Okay, and so we have with the tools at hand, I can set this up, creating the pathway whereupon I can set up an integrating factor. So we got dx over dt plus x over 200 is equal to 5. Okay, and just let me mention something here. Now, you're not looking at dy over dx, so you got dx over dt and so we have plus p of t x is equal to q of t. So we're looking at a first order linear differential equation, and this time where the dependent variable is x. Okay, so it's linear first order, and here we have x of first degree. All right, so setting things up in terms of an integrating factor, so we have the coefficient p of t will be the fraction 1 over 200. And for what we have in terms of the integrating factor, so you have e to the integral of p of t dt, and it's going to be e to the integral. So you have 1 over 200 times dt, so you have the integral of dt over 200, and the antiderivative, okay, you see we have e to the t over 200. So this will be the integrating factor, and we will multiply the terms from the standard first order linear differential equation setup. Okay, so we got e to the t over 200 dx over dt okay, so we have plus e to the t over 200 so we have over 200 times x is equal to 5 times e to the t over 200 And once again, we have for the left-hand side, okay, this will turn out to be the product rule expansion of taking the derivative nt of the product that we have as we multiply the integrating factor and the dependent variable. And we have to the right, okay, so you have 5 times e to the t over 200. And removing the brackets, so I'm going to integrate on both sides with respect to t. And here we have 5 times e to the t over 200 dt. Right. So for what we have at this juncture, okay, so you got e to the t over 200 times x, and integrating with respect to dt, or the variable t, you have e to the t over 200. Now again, okay, now if I were to take the derivative, I would be multiplying by 1 over 200. But since I'm integrating, or taking the antiderivative, I'm dividing by 1 over 200, which means that I'm multiplying by 200. And 200 times 5 becomes 1,000. So we have 1,000 times e to the t over 200 followed by the constant. Now, looking at solving in the general case for x, so dividing by e to the t over 200. For the first term, I have just 1,000. And then dividing by e to the t over 200, that will be the same as multiplying by e to the negative t over 200. So this is the general setup. Okay, now, for what we have in the case of initial conditions, okay, again, you have the mixing tank consisting of 100 kilograms of salt. Okay, so this will be at time 0. So you have x over, or I should say x of 0 is equal to 100. Yes, you have initially have 100 kilograms at time 0. So your x is 100. Whenever t is at 0, and guess what? We have e to the 0 is going to be 1. And guess what? If I take 1,000 away from both sides, we have that c is equal to negative 900. So, looking at what we have for any time t, now that we have the value of c, we're going to have this equation becomes more specifically 1,000 minus 900 times e to the negative t over 200. Now we're looking at how long it's going to take for the amount of salt to be 900 kilograms. So I have x of t is equal to 900. And filling in, okay, so you have 900 for x. And so we have is equal to 1,000 minus 900 times e to the negative t over 200. And isolating, okay, the variable expression. Okay, so if I take 1,000 away, so I have negative 100 is equal to negative 900 times e to the negative t over 200. And if I divide by negative 900, so you got a negative over negative is a positive. So you had that 1/9 is equal to e to the negative t over 200. And I can take care of the e, so I can take the natural logarithm of both sides. And for what we have in the case of the natural logarithm of 1/9, okay, you have among the first digits, you got negative 2.197, and that's equal to negative t over 200. And multiplying both sides by negative 200, it's going to turn out that for the time, okay, we had that t is going to be about 439.4 seconds, and to the nearest minute and second, so we're looking at 7 minutes and just over 19 seconds. And so that's about how long it's going to take for the amount of salt to go from 100 to 900 kilograms.